All right, so in the previous video, we just finished up on an example problem. I've gone ahead and written the example problem here. I'll read kind of how this example problem would probably be written. It would say something like you've got um, a Carnot refrigerator, a Carnot refrigeration cycle, where the the external space, the high temperature reservoir, which we're going to reject heat to, is at 25 degrees C. So that would normally be like the kitchen space or the inside of a house, maybe. Um, I guess, yeah, the inside of outside of the refrigeration unit would be 25 degrees C, and the net power, or it might say that the compressor consumes power at a rate of 500 watts. It's not a terribly large compressor. Um, and in this case, they give us the coefficient of performance for this reversible refrigeration cycle is 4.5. And the problem is going to ask us to determine the rate at which heat is being removed from the refrigerated space and also what is the temperature of the refrigerated space, given the information that we have. So I would always ask students, okay, where do we start? What's a good place to start? And it's when you're trying to find a heat transfer, a lot of times the common gag reflex at this point probably is the first law. And then now I would say, okay, well, first law for what? And when you look at the first law of, and somebody might say, well, what about the first law for the fridge? Okay. So to write a first law equation, we draw our system. You could draw the components if you want to draw it. I'm not going to. I'm just going to say it's fridge. It's refrigerated space. What do we have? We've got Q dot L. I've got the power input, and I've got Q dot H. Okay, so if I'm trying to find Q dot L is going to equal Q dot H minus the power input. Right? And I've skipped a step here. It would be Q dot L plus work in minus Q dot H equals 0. And I would solve for Q dot L and say, okay, well, how many equations and unknowns do I have? Well, I don't know QL and I don't know QH. So this one doesn't, I do know the power input, but this one doesn't get us there. And a lot of times in some of these problems, we might know something about, like if I knew some information about the condenser, maybe I could use that to find QH, and then QL is my only unknown here. But unfortunately, in this case, I've got two equations, two unknowns, and I don't think I've got enough information to find this other unknown. So I think I'm kind of stuck at a dead end with the first law. Sometimes that happens. It's betrayed us for once, right? So okay, well, what else do we know? Do we know anything else that would help us get to Q dot L? Well, sure, actually, you know the coefficient of performance. You know the coefficient of performance for this reversible cycle is exactly 4.5. By definition, that Q dot or that COP is what you want. It's a performance ratio. It's what you want, your output, if you will. That's Q dot L divided by what you have to do to get it. That's the work input, which we know. So I've got 4.5 is equal to an unknown divided by a known quantity. And therefore, I can find Q dot L is equal to 4.5 times the power input. So that's a known value we can find. Okay. That's one of the answers we're looking for. What else are we looking for? We're looking for the temperature of the refrigerated space, right? What is this space that we're cooling and we're kicking heat into the high temperature space? But we don't care about the high temperature space. We want to know what is TL. We want to know what's the temperature of this refrigerated low temperature space. Okay, well, remember, because this is reversible, that coefficient of performance is only dependent on the ratio of temperatures. Now we got to go to the right equation that has this, and well, I can derive it right here. I can plug in for work in. Work in is equal to Q dot H minus Q dot L. So this is 1 over Sorry, I'm deriving in my head. Um, 1 over, it's going to be Q dot H over Q dot L. I don't have these memorized because I know I can derive them pretty quickly. Hopefully, I'm not making a mistake here. And then again, the ratio of heat transfers is going to equal the ratio of temperatures for a reversible device. So I know COP is 4.5, and I know TH. I can now find TL. I could do some algebra, but I can now find TL. And so I'd ask people, okay, what is TH, right? So if I solve for TL, let's do this one. 1 over 4.5 is equal to TH over TL minus 1. And however you do your algebra to get to TL is fine with me. Okay, so 1 over 4.5 plus 1 is equal to TH over TL. And now TL, what I'm looking for, is equal to TH over quantity 1 over 4.5 plus 1. I think that's right. I may have made an algebra mistake in there, but I'm pretty comfortable with that. So I'd ask the class, okay, what is TH? And somebody would say 25. I said, okay, what is TH? And somebody might say 25 Celsius. And I said, yes, what is TH? I can't use Celsius here. I have to use Kelvin. What is that? 298 Kelvin? 298 Kelvin divided by, if I've done my algebra right here, feel free to roast me in the comments if I haven't, and you can calculate this out. I'm not going to. You can. I would encourage you to pause it here and calculate both. Pause it here and calculate both Q dot L and TL. And you don't have to trust my algebra. Feel free to practice your own algebra. You should be. Keep you engaged. And I'm going to show you the answer. So pause it here if you haven't already got an answer. Okay. There's Q dot L, 4.5 times 0.5 kilowatts is 2.25 kilowatts. And then, yeah, so solving for T sub L, you're going to get about 243, 244, about 244 kelvins, which is a negative 29.2 Celsius. Okay. All right. I'm going to stop there. We're going to pick up that on the next example. We'll look quickly at this example in the next video.